بشكر كل عالم وباحث ومجتهد، وبدعو لمزيد من الجهد والبحث من أجل مصر، من أجل مصر.
دلوقتي هنتكلم عن حاجة كيمستري وايز، هنتكلم عن البوليمرز. وعشان أسهل على حضراتكم هتلاقوا في كل سلايد أنا واخدة فيها ريفرنس من حتة، هتلاقوا فيه باركود. فسيبلي حضراتكم ممكن تصوروا الصورة وبعد كده الباركود لما تعملوه سكاننج هتطلعوا البيبر على طول. اوكي، فده عشان يسهل ليكم يبقى عندكم السورسز زي ما انتوا عايزين. فالموليكولار imprinted polymers, I will give shortly some information about the basics of imprinting and their common applications. By molecular imprinting, we are having a technique that designs and tailors specific polymers with a memory effect for a target molecule. وعشان كده دايما بقول anatase polymers. So the main idea of these polymers is to have the lock and key. The lock acts like the polymer, and the key is exactly the template. So you have a very specific polymer that you can use later on for combination with your template. The synthesis process for the polymer is simply an interaction between the polymer itself or the template with its functional groups with the monomer itself according to the reaction centers that are present in both of them. After this, we allow them to combine together. Each one is attracted to its own equivalent center, and in order to keep this frame constant, we use a cross-linker, and after cross-linking the polymer, we got this structure. This structure is very important that you can use it for drug targeting. You can load any kind of drugs, anti-cancer drug, antibacterial, or whatever, and you can use it later on for drug delivery. If you extend your work by removing the template by specific reactions, you end up to have a recognition site, and you can use this recognition site later on for sensors applications and for water treatment applications and for any kind of solid phase extraction. So these polymers offer a lot of variable advantages. They are resistant to all types of mechanical solvents. They are very similar to natural receptors, and they have a very high loading capacity, and they are reusable. And this is very important because we want to reduce the amount of chemicals that we are using and the repetition of the chemical experiments. If we look to the trends in the application of molecular imprinting, as you see, 20 years ago it was something like 29 or 30 month applications, but right now in the past 7 years we can say that we are reaching something like 100 times of this number, because we started to include a lot of applications for molecular imprinting. To give quick example for the different types of imprintings or applications, we can say that we have a separation of different natural products. You can select just a component in a natural product and exclude all the other components. And this is a dream for the people working in pharmaceutics due to the activity of some natural products in cancer therapy, for example, or their activity as antioxidants. On the other hand, we can use them for separation between enantiomers, use them for removal of pesticides and toxins in environmental hazardous samples. We can use them for sensors and diagnostics, and I will show you an example that we made in our lab for the detection of COVID and some other important viruses using a simple approach. And finally, this is an attempt to have drug delivery. They are starting to use the polymers for drug delivery, and I will show you some good examples for their applications. In order to have the polymer, we have three main components. The first one is the functional monomer, and we have to select it according to the properties of the template and what kind of reaction we want to proceed. Or we need to have, the second component is the porogenic solvent, and like the solvent we can control the depth and the size of the pores that we have inside the polymer itself. And we need to use them, or we need to use a cross-linker to keep the polymeric matrix constant. So these are basically the main components that we have. To start out designing a polymer, we use molecular modeling, and there are a lot of computer programs that you can use to select the best polymer to use, and even you can design the structure of your polymer and calculate the moles between the atoms and each other, and by this we are able to divest what kind of interaction we can use the polymer for. Here is a simple example for two estrogen forms, one for the male and the other for the female, and the elevation in the levels of these estrogens are indicators of ovarian cancer or prostate cancer. So by having a polymer to detect this elevation, we can be able to differentiate, or we can early detect the possibility of having cancer. So just using computer programming, we were able to define which kind of monomer to use for the polymer preparation, and by doing such calculation, we reached this complicated shape. This complicated shape represents how the polymer molecules interact with each other. To make it simpler, we have here an example for chichoric acid. Chichoric acid, this is a natural product present in a plant known as chicoria, and it has antioxidant properties. If you look to the structure of chichoric acid, we find that there are two hydroxycinnamic acids connected by tartaric acid. So that's why natural product موجود في الشيكوريا. والشغل ده احنا كنا عملناه مع حد من الولاد في الجامعه الالمانيه، والحقيقه اغلب الشغل هيبقى معمول في زويل والجامعه الالمانيه وحبه حلوين في جامعه القاهره. فالشيكوريا قلنا ليها antioxidant properties. If we look to the structure of chicoria, we can say that this is considered as an acidic molecule, so to increase the possibility of electrostatic attraction, we use a basic monomer. And if we look to the structure of the basic monomer that we have here, we have a nitrogen group. So this means that nitrogen is electron attractive, or it prefers to have a hydrogen bond, or it's a hydrogen bond acceptor. So that's why when we look back at the structure of chichoric acid, we find that there are 6 possible centers that we can use for interaction. We excluded the two in the middle because they can form intramolecular hydrogen bonding, and this means that we can say that the best form for this molecule to form a polymer is to include all hydrogen bonds. And finally, by calculating the binding energies, we proved this, and we found that the best ratio to prepare this polymer is 1:4, and this is how it looks like. So, هو شغل حالا تقلقش وليه دعوه بكل حاجه. يبقى we can start preparing the polymer, and we want to prepare the molecule, so we use quantum mechanics in order to design the polymer itself. And then we go to the different science approaches that we can apply. We have very different types of approaches to be applied, but the 4 most common of which are these 4. The simplest one, which is, you can say that like 70% of the publications in literature are based on pulp polymerization. So pulp polymerization is just mixing the ingredients together, cross-linking them to get a pulp of polymer, and then you grind it just using a mortar, and after this you need to sieve it in order to control the size. Unfortunately, when you use the polymer for HPLC applications, you need to have a specific exact size of the particles that should not exceed 20 micrometers. If it exceeds this size, there is a probability that you have a back pressure, and this will spoil your HPLC experiment. So, unfortunately, pulp polymerization is not that best choice for HPLC applications. So that's why we move to other types of beaker polymerization that can be used to control the size, like emulsion polymerization or precipitation polymerization. But these methods, they have the problem of using a huge amount of reagents, and that's why they are not environmentally green. In order to have interoperability, we started to have an approach known as surface imprinting. And by surface imprinting, we can prepare the polymers on the surface of a magnetic iron particles, and just using a simple magnet, you can collect your stuff together, and you are ready to remove your contaminant. That's why the use of magnetic particles have a lot of application in environmental treatment. If you have a sample contaminated with heavy metals, prepare a magnetic polymer and connect your contaminants in one experiment, simple experiment. The next choice is based on sensor application, or it's more for sensor applications. Here we have an example for an electrochemical sensor for the detection of verdenafil. Verdenafil, this is another pharmaceutical compounds used for male erectile dysfunction like Viagra. But usually it's overused in the market, and a lot of people take a lot of vardenafil or sildenafil, so just having a sensor to detect the extra dose, it will be more easy rather than just doing the practical methods of extraction and then after this using HPLC. So in this approach, we just deposited a layer of the imprinted polymer on the surface of a sensor, and then by doing some chemical experiments, we remove the template, and it's ready once more to rebind to the template, and by this you can do the experiment just in few seconds. So instead of doing the lab experiments in hours, you just do it in few seconds. According to the type of interaction, whether it's covalent or non-covalent or semi-covalent, or it's on a kind of metal or nanoparticles, or the method of preparation, you can end up to have many applications for molecular imprinted polymers. The first important application includes solid phase extraction, and for solid phase extraction we can use it for extraction of natural products or environmental contaminants. All you need to do is cast your sample, first condition your polymer in a cartridge, the simple cartridge that is shown here. This is the setup for the system. So it's just like a syringe, and in this syringe we fill up with the polymer, and then after this we need to condition the syringe, and then after this upload the sample, remove any other components present in the sample, and finally you have a cartridge loaded with your contaminant, and you can use it for quantification. Solid phase extraction works for small molecules, like for example nitrophenols, and it works for big molecules like the toxins, and it's able to differentiate them. And it works also for heavy metals detection, but in this case you can either imprint the complex of the metal or imprint the ligand itself, and then we will follow up that combination and interaction between the metal and its ligand. There are a lot of examples of successful imprints in all fields, including pesticides, proteins, drugs, and natural products, and that's why a company like Sigma Aldrich is commercially developing or selling molecular imprints for many commonly environmental hazards. And if you want to design a specific polymer, you can go to a company like Biotech. This is a chromatography company, and you can tell them that I have the following template. I want to have a cartridge selected for this template based on molecular imprint, and they do it for you, but you will pay a fortune of money to reach this way. The next very common application from molecular imprints is the biosensors and electrochemical sensors. In order to describe the idea of any biosensor, we usually have a metallic surface that we use as a molecular recognition site. We modify it with whatever, and then we can have a signal related to a reaction that occurs at the surface of the sensor, and it ends up that we have an output in the form of electrical signal. This surface can be either a carbon-based material, or it can be a holder for this carbon paste. It can be a metallic electrode, and right now, preferably, we like to use the screen-printed electrodes. In order to get the difference between using the regular electrodes and the screen-printed electrodes, when you are doing a lab-scale experiment, you are doing it in the lab, you are using a huge instrument. This is like the size of the old computers, and you have 3 electrode system, and this instrument costs something like 1 million Egyptian pounds. But right now, people are going to miniaturization, so that's why we said we are using a portable electrochemical device, and we tend to have the screen-printed or even the patch sensors that you can just put it on the patient, and you can track all the time the variations that happens in the levels of the metals, or even, as you will see later on, the biomarkers or the stress variables. So, right now, we started with solid holders, and we ended up to have screen-printed electrodes that are very tiny inside, and they are flexible and wearable, and you can use them and move all the time. So what about molecular imprints? What are they doing in this story? So as we see that at the surface of the electrode that we are going to modify, we can have any kind of modifier that is selected staying part, so the molecular imprints can come here. There are molecular imprints for large molecules or for tiny molecules like pharmaceutical compounds, and right now we are having even virus imprinted molecules, and we can do cell imprinted polymers, so you can do whatever imprint for anything that you want to do. So in order to get an overview about this, we have here bisphenol A. A lot of us are using plastic bottles, and we have to check before using plastic bottles that they are bisphenol free. So here is an example for a sensor design in our. It's not about the bottles that we are using, but we can get bisphenol through contact with the very simple sheets and the receipts even that we get from the supermarkets. We found that they are having bisphenol A. So we have to be careful. After using these receipts, we have to wash our hands carefully because they are full of bisphenol A. Bisphenol A, by the way, is very close to destruction of estrogen, so that's why they are calling it hormonal destruction material. Another important example is the pesticides. So the pesticides, I'm getting fast. I'm running, صح? طيب. 5 minutes. So for the detection of pesticides, أكتر من كده هتكلم بسرعة صاروخ في الثانية. So for detection normally of pesticides, we need to use a very expensive equipment, which is the LC mask, because most of the reagents of the pesticides are either UV inactive or HPLC inactive. So that's why we are not able to detect them except using tracing their mass. In the simple way of application of MIPs, we are able to design a sensor based on a specific selector for these pesticides, and we can do it in a form of the screen printed chip that we can use it to get a readout through a mobile phone. So just instead of having such a huge equipment in the farm or wherever, you are simply designing a sensor that you can put it in your mobile and you get the reading without any problems. Just 3 days ago, we got an acceptance for such a work in Food Chemistry Journal, and this is a journal with high impact factor. It's 9 point something, and for sensors, I think we can consider that this student is very lucky to have such a publication. But it's not about pesticides and it's not about natural hazards, but we can use also molecular imprints for cortisol, which is considered as one of the stress factors that we can follow. And we can use it also for other stress factors. And this is very important for athletes. When they are performing, they need to follow the levels of the performance of their stress conditions while practicing, so that they know that they did an overload or not. And this is very important because many cases were reported that they died because of doing extra exercise. Also, we have examples for biomarkers. So instead of doing the genetic tests and the histological tests that takes a hell of time and they are very expensive, we have an example, but this is not our work, of course. It's designed for sarcosine, and sarcosine is one of the prostate cancer biomarkers. I can tell you frankly that prostate cancer, this is the worst type of cancer affecting males throughout the world. So having just a sensor and a test that is accurate to quantify how much sarcosine is there, this is a good indicator and fast indicator to diagnose cancer. It's not about just one kind of cancer. There are a lot of cancer markers that have reported in literature, and they have their biomarkers. We can also use it for detection of bacteria like the E. coli, and we have another example for, I think, Staphylococcus or something like this. And here we have this work was done by one of my students, and she's working in collaboration with Wales City, and we do it for foot and mouth disease. Foot and mouth disease, ده الحمى القلعية. Okay, so in Egypt we have a lot of farms that were infected with الحمى القلعية, and in order to diagnose الحمى القلعية, you have to do an ELISA testing that takes around 24 hours. And foot and mouth disease, this is a very fast propagating virus that can infect the whole farm within a few hours. Here, when we perform this application for foot and mouth disease sensor, it takes us within 2 minutes to get a feedback that we have an infection, and we can quantify the level of infection with foot and mouth disease. And we did this for 2 prototypes that are available in Egypt. We have here O type and we have SAT2 type, and both of them were rewarded a patency from the Egyptian Academy of Science and Technology. It didn't stop only to this point. We moved for SARS-CoV. During SARS-CoV 2020, it was hard to discover the infection, and you have to do the PCR test, and it takes 24 hours, and then we can have a lot of complications. But in our case here, we just simply take the swab, dissolve it in a buffer, put it on the sensor, and get a result that is accurate within 5 minutes. So you are doing something. والله يا دكتور كنت عايزة. Okay, so for these kind of sensors, it's very fast. So finally, the last type of application, this is for medicine. As you know, when you get a dye, an eye drop, you just put it in the eye drop, and what happens? Most of the drops spill out, okay? But on doing or on having a loaded contact lens with the nibs, this controls the release of the drop, and this is, of course, is more economical. We all know that the dyes are the drops are very expensive, and it also works for transdermal patches. This is another route of using the polymers. And the last thing, which is very important, is insulin. We have a high rate of diabetic patients in Egypt, and of course, many of them are under insulin injection, and this is not comfortable for patients. So that's why there is an attempt to prepare an imprinted polymer. But of course, this is a problem because insulin is a protein that is going to be digested in the stomach itself. So the main challenge is to try to prepare the polymer and control its release within the stomach. And because the diversity of application and the increasing number of people working with molecular imprinting, we have our own special database where you can get what is new, and still a lot of work to do in order to reach a super powerful molecular imprints. And finally, I would like to thank my team in Cairo University. These lovely students have made it live. Most of the publications presented in this presentation are made of them, and we did this only in 4 years. In 4 years, we have something like 40 publications in different disciplines and fields. And I would like to thank the organizing committee for such an invitation. I'd like to thank our godfather, I call him my godfather, my god uncle, Dr. Seyedmechan, for the nice presentation. Thank you all for listening. It's time for a coffee break. Last reminder, الناس اللي ما سجلتش في رحلة الكلاس بوت، خلاص احنا كده وصلنا للعدد ونفسنا تبقى معانا. الساعة 1 هيبقى في جروب فوتو هتبقى عند اللوب. اوكي؟ بس Thank you so much for this very fast lecture. Dr. Reda and Dr. Rasha. I'm sorry, Dr. Reda, we postponed. Where is Dr. Reda? Somebody wanted to ask you about the lecture. So can we do the discussion now, very fast discussion before the coffee break, if anybody has a question? ربنا يبارك في حضرتك. اولا العظيم اللي انت بتعمله ده 5 دقايق اسرع برزنتيشن. لا واشرافك الفقاعه والكيميائى والناس اللي كانت صحيح يعني